Değerli konuklar, VitrA'nın İngiliz Kraliyet Mimarlar Enstitüsü RIBA İşbirliği ile Eylül 2018'den bu yana düzenlediği Mimar Sohbetlerinin 23. buluşmasına hoş geldiniz. RIBA'nın Londra'daki merkezinde gerçekleştirilen ve Birleşik Krallığın farklı şehirlerine taşınan etkinlik kapsamında uluslararası mimarlık camiasının öncü isimleriyle çağdaş meslektaşlarını ağırlıyoruz. Ve her yıl Türkiye'de de bir etkinlik gerçekleştiriyoruz. 2019'da Daniel Libeskin'i de İstanbul'da ağırlamıştık. 2020'de henüz pandemi başlamadan önce ise Ben van Berkel'i ülkemize konuk etmiştik. Yaşadığımız dönemin koşulları nedeniyle RIBA ve VitrA Mimarlık Sohbetlerinde 2021'e online bir etkinlikle merhaba diyoruz. Bu vesileyle yeni yılın tüm dünyaya sağlık, huzur ve mutluluk getirmesini diliyorum. Bugünkü konuklarımız Heneghan Peng stüdyonun kurucularından Róisín Heneghan ve Shih-Fu Peng. Heneghan Peng Mimarlık Ofisi 3 ay önce Kraliçe 1. Elizabeth tarafından 1592'de İrlanda'nın başkenti Dublin'de kurulan ünlü Trinity College'ın yeni ziyaretçi merkezi ile 200 bin eski kitaba sahip tarihi kütüphanesinin yeniden tasarlanmasını üstlendi. Sözü kendilerine bırakmadan önce bu etkinliğin ev sahipliğini yapan VitrA adına Eczacıbaşı Yapı Gereçleri CEO'su Özgen Özkan'ı ve RIBA adına bu etkinlikleri düzenleyen Kamusal Programlar Yöneticisi Chloe Spiveylo'yu yayınımıza davet ediyorum.
Değerli konuklar, sevgili dostlar, hepinizi sevgi ve saygıyla selamlıyorum, hoş geldiniz. VitrA markamızın 60 yılı aşkın geçmişi boyunca bir yandan daha sağlıklı bir yaşam için ürün ve çözümler geliştirirken, bir yandan da aynı ufku paylaştığımız mimarlık ekosisteminin gelişimine katkıda bulunacak çalışmalar yapmaya gayret ettik. Bu kapsamda kimi zaman değerli projelerin ortağı olarak, kimi zaman da kendi projelerimizi oluşturarak mimarlık kültürünü destekledik. Bunu sadece öncelikli faaliyet alanımız olan Türkiye'de değil, üretimimizin %80'inden fazlasını ihraç eden bir grup olarak yer aldığımız diğer stratejik pazarlarda da sektör profesyonelleriyle diyalog kurmamızı sağlayan çalışmaları destekleyerek yaptık. Venedik Mimarlık Bienali, İstanbul Tasarım Bienali gibi. Bugün bu yayında bizleri buluşturan RIBA ve VitrA ile Mimar Sohbetleri de bu çalışmalara bir örnek. 2,5 yıl önce başlayan bu yolculuk İngiltere'de olduğu gibi Türkiye'de de büyük ilgi gördü. Bunun için son derece memnunuz. Bu arada gururla belirtmek isterim ki pandemi sebepli bir gecikme olmaz ise Mart ayı gibi çok kısa bir süre sonra VitrA Londra Showroom'u, zaten tasarım ve mimaride dünyanın merkezlerinden biri olan Londra'nın tasarım ve mimarinin merkezi olan semti Clerkenwell'de açıyoruz. Ve pandemi sonrası bu toplantılarımızın birini de oradan yapmak istiyoruz. Bu değerli etkinlik dizisi için RIBA ailesine ve programa katkıda bulunan siz değerli mimar dostlarımıza VitrA adına teşekkür ediyor, iyi seyirler diliyorum. Görüşmek üzere efendim.
Thank you. Welcome again and thanks for joining us for this digital talk as part of our prestigious RIBA and VitrA Talk series. My name is Chloe Spiveylo and I work at the Royal Institute of British Architects in London as the Public Programmes Manager, where I lead on programming and delivering RIBA's public talks and events. The RIBA is a global professional membership body driving excellence in architecture. We support our members and society to deliver better buildings and places, stronger communities and a sustainable environment. We have over 47,000 members across the world and nearly 6,000 of them are based outside of the UK. If you are interested in joining, we have varying membership options, including joining as a RIBA affiliate member or as a RIBA chartered member. So if you are interested, I would advise you to find out more via our website, www.architects.com/join-RIBA. The RIBA is unique in being both a membership body and an accredited public museum. We have over 4 million items in our British Architectural Library, which is free and open to everyone. We use our collections to curate a number of free exhibitions across the year, alongside commissioning new displays and installations by architects and designers who provide a contemporary response to our historic material. The RIBA and VitrA Talk series sits as part of our public offer to architects and society, providing a platform to hear lectures by emerging and established architects from across the world. In this slide, you can see the talks we've delivered as part of this series since our last talk in Istanbul in March with Ben van Berkel of UN Studio. The world has completely shifted since this lecture, so in fact, all these talks have been delivered digitally. Since September 2018, when this series started, we have had 44 speakers from 14 different countries and a combined live audience of over 7,500 people. Many of our talks are still available to watch back online via RIBA's YouTube channel. We have a dedicated RIBA and VitrA YouTube playlist, so I do encourage you to watch them. But back to today's talk, I am very happy to be introducing Róisín Heneghan and Shih-Fu Peng of Heneghan Peng Architects ahead of the lecture today. Heneghan Peng is a design partnership specializing in architecture, landscape, and urban design. Founded in 1999 by Róisín and Shih-Fu in New York, the practice has since relocated to Europe with offices in both Dublin and Berlin. The practice has become well known for its ability to produce buildings that seamlessly embed innovative and contemporary architectural design within complex historic sites. And they have won numerous international awards and competitions, including the prestigious 2019 Aga Khan Award for Architecture. We are incredibly lucky to be joined by both co-founders, Róisín Heneghan and Shih-Fu Peng, tonight. Shih-Fu will deliver the lecture, and we will be joined afterwards by both for a short Q&A with questions that you've sent in to us in advance. Shih-Fu, over to you.
Thank you, Chloe. I will forward it. So this is actually a lecture or talk, I would say 20 years in the making. It's about the grid. And as most architects would know, that a grid is something that would occur in every plan, in every drawing, and that it is throughout the years. It's a convention of architecture. What we like to talk about is how that particular convention has evolved within our office. And that particular convention engages, it's very much a collaborative convention, because it's not something that we alone actually have evolved. It is something that through working with some key people in different offices, such as Francis Archer at Arab and Tom Gray at TESS currently, and Tim McFarlane at DUMAC previously, and currently Glass, that have developed over the years. So to start with, we've always thought that we always saw it as, or at least it's what it's been evolved as, is a common language. It's a common language in terms of the kind of the collaboration between the architect on you see here on the left-hand side, and then the engineer, which you see on the right-hand side. The best example of this is when we did the bridge for the London Olympics. We worked with Hanif Kara of AKT2 currently. And this is a cross section to the bridge, which is a triangle. And we sent our geometry over to Hanif, and we said that here's the bridge. Let's look at seeing if the very thin cross section could span the Carpenter's Lock. And what happened was, interesting enough, by the time we got to the competition, that they came back and said, "Oh, no problem, it works." What we discovered immediately after we won is that the triangle that the architect took, the exact same triangle, was actually the skin of the bridge, which is the architectural component. What AKT took as the triangle are their centroids, which is the grid. And in structural terminology, that is very much what they would use for analysis. The best part about this is the engineering component doesn't actually fit into the architectural component. They both desperately desire to occupy that same triangle in the exact same place and time. Obviously, we got it working in the end, no problem. But it's this kind of disjunction that somehow we believe that the grid is very successful in addressing. So this is just a basic diagram saying, the degree of architecturalness. So on the left-hand side, you have low architecturalness. On the right-hand side, you have extreme architecturalness. And the extreme architecturalness are what we would call iconic projects. The funny thing about the whole thing is that, oddly enough, the more architectural a project becomes, the less engineering it becomes, that somehow they literally work in exact opposites from each other. And is there somehow a happy meeting point between architecture and engineering? So this diagram just some random buildings we picked at that time. This must have been 10 years ago at this point. On the right-hand side, we see at the upper right corner pedestrian bridges. The thing about pedestrian bridges is it has actually very low loads. So to a large extent, architects or designers can do pretty much anything they want, and it'll probably make the span over the river. On the upper left-hand side, we see road bridges. And the trouble with them is that the calculation is that one must allow for a calculation such that you have a caravan of trucks, all of which are loaded solid with construction materials. First truck breaks, every truck breaks subsequently, and that twists the entire bridge with an amount of force that is inconceivable by most architects. So you can see on the projects like that, pretty much is in the remit of engineers. And the point behind this is there's some way we can actually allow the two to occur in the middle. This is a great view of, and I forgot the project, but anyway, it's Corbusier. Oh, yes, it's the Olsenfant studio. We think it's a great photograph that actually begins to illustrate the kind of dichotomy between the two. And I just put a line down the middle. So Corbusier doesn't talk about it, but if you actually very quickly, if you look at this photo, you'll start to see a few key things that start to pop up. The architect is actually on the left, and the engineer is on the right. The architect, the space of creativity is in this kind of dark room that is hovered above the ground, and inside this kind of dimly lit or almost mythical space that nobody can see what's going on is where creativity occurs. On the other side of that, you can actually see the engineer. Everything is bright, everything is transparent, everything is clear, and somehow everything just seems to make sense. There's no myth, because at the end of the day, it just is clear and light. On the kind of left-hand side, you can see that if an architect tries to do a painting where you see the yellow arrow, the bottle is even confused between what is black and white. On the right-hand side, you can see a straight edge, which draws perfectly straight lines. On the left-hand side, in the cyan arrow, you can see a fireplace, traditional hearth, warmth. On the right-hand side, we have engineering at its finest, gun tube radiators working perfectly without having to light the wood. And you can see this going on in the image as he points out different things. The ladder on the left-hand side, the staircase on the right-hand side, the very heavy column on the left-hand side in red, and the very light spindly column that holds up the kind of skylight or the window on the right-hand side. So there's a kind of clear disjunction between the two, and the notion is that can the grid bring the two together. So regulating lines. So where obviously this has its kind of history. It just goes back and back further. I mean, in history. On the left-hand side is Palladio. On the right-hand side, is actually Garches by Corbusier, and you can see the red lines, which talks about an AB organization of the grid. And very much so. Obviously, it's much looser for Corbusier, but those red lines are very clearly the structural lines that we keep the building up, and simultaneously they create a rhythm between what is kind of primary and secondary, at least going north and south within each building, and a kind of triptych organization in both directions. So one can begin to see that the grid can be both architecture and structure simultaneously. The classic modern example of this is Khan. His engineer commandant have within every single one of these buildings very much described that architecture and structure cannot be separated. The prime example is the Salk Institute. Here you see the kind of varying deal trusses, that space in between the open labs. And effectively, in the kind of sectional level, that the grid, which is the level planes of the kind of truss zone or the service zone, very much describe both the structure of the building, which kind of creates these columnless space, but simultaneously also the service areas that would serve both above and below. One of the first things we've done, and we've developed this both with Tom Gray as well as Francis Archer, is that that somehow to remove that kind of mythical emergence that on the left-hand side of Corbusier's image, that somehow this creativity can only lie within the body of one person, is to somehow kind of coded. disentangle it. So the points are no longer embedded in one's brain, but embedded within a mathematical precision. So what this begins to describe is that if you start at 0, 0 in the lower left-hand corner, and we created a grid which is 3 by 3, and provided that we don't actually use angles and create lines of different ratios, whether it's 1 to 2, 1 to 3, 3 to 3, and so forth, and conversely, and if we actually were to find the intersections between each of those lines, that particular pattern there is no longer hidden in the dark, but very much precisely derivable through mathematic formulas between two ratios. And there's absolutely nothing mysterious about it. And what's interesting, what this begins to show, that if you find the intersection between two ratios, and Francis Archer can actually do this in his head, that the XY positions of over 90% of the points are actually real numbers. They are not imaginary numbers with funny things after it. So you can pretty much know where any kind of seemingly random form is in three-dimensional space by understanding the relationship of two ratios. And the next one just simply shows that you can do this in 3 dimensions, which is what we did in Egypt, that you can intersect the lines in 3-dimensional space. And interestingly enough, those points in 3-dimensional space, which seemingly is random, can also be derived as perfect numbers, perfect X, perfect Y, perfect Z, for over 80 to 90% of the numbers. So again, they are no longer mysterious. All you need is an understanding of the relationship between a cube, which is 3 by 3 by 3. So how does that get developed? In GEM, which is when we first met Francis Archer under Cecil Belmont, we won the project when we were 3 people in the office. It's $1 billion project. It's 1 million square feet. It's a big project. I mean, even for large offices, it's a tough project. And somehow we had to figure out a way that we can coordinate effectively and efficiently a project that will have thousands and thousands of drawings. And that's something we set about to develop with Francis as far as for this project, the grid. So over here, you can see, this is just an illustration on the lower right-hand corner. You can see that the 3 pyramids, any 3 points describe an arc. Here, you can see that the pyramids describe an arc from the lower right-hand corner. And the museum on the upper left-hand corner is actually kind of a mirror of those 3 lines. The concept being that the museum actually inscribes within its galleries all 3 pyramids, which are the most important artifacts. So we'll touch on the architecture, but because that's not really the point of the talk, I'm going to try to just hit a few bullet points. The Nile is described, Egypt or the Nile is described by 2 starkly juxtaposed conditions. That of the desert plateau, which is approximately 60 meters above that of the Nile Valley. The Nile irrigates the Nile Valley at the lower level and creates an intense greenness. And everything we know to the left and right of the Nile as one extends beyond the kind of lush green Nile Valley will be the desert plateau, meaning the tombs, Tutankhamun, all of that of death will actually occur within the desert, and that of life in the Nile Valley. Here you can see a cross-section through the kind of geographic landscape, which is both important geographically and symbolically. You see the Nile in the middle. To either side where the trees are is the Nile Valley, and lifted on 60 meters above to either side would be the desert plateau, on top of which the pyramids would sit. The site is actually fantastically located. It's located precisely at the point where the desert plateau would rise and the Nile Valley would end. So again, just by the mere selection of this site, it very much, which would house Tutankhamun, it would very much describe the kind of geographic and symbolic importance of this kind of geological condition as something that very much described Egypt all through its history. So As far as the grid is concerned, the most important thing of any grid is to set the origin. So regardless of anything, we need to start somewhere. We set it on the upper left-hand corner where you see the lines occur. It is actually in a traffic roundabout. The client didn't like that, but you don't really see it in the end, so maybe that would work for him. So we fan these, we fan out this kind of line. The first line actually is precisely the line where the 20-meter sectional condition would occur, is where the Nile Valley would stop and the desert plateau would arise. And from that kind of geological condition, we fan out the museum to capture all three pyramids within its kind of space or body. It is a museum, it is a chronological museum, so overlaid onto the site is a chronological series of horizontal lines going from the most modern times to the lower portion of the screen, which is the latest, the furthest back in history. And those would effectively be also the grid lines. Here you can see on the left-hand side is the line that is between the traffic roundabout and the tallest of the pyramids, and how it fans, and that again is the kind of cliff face or sectional condition as it fans out to capture all three pyramids. We actually also in section connect the museum to the top of the tallest pyramid. And the funny thing about this is that in order to get our perfect numbers, we actually have two drawings which connects to the top of the pyramids. One which is the architectural drawing, which connects this kind of mysterious height with a funny number that we can't figure out why. And the second drawing with the red line actually connects to a perfect number, which has all zeros after that. We use the perfect number drawing for the construction set because it produces perfect numbers in the museum. And we use the funny number one for the client because it has to be architecturally mythical and connected. One saves money, one costs money. Nobody can tell. So this is the view of the museum from above with the kind of the fanning roof that goes out to the pyramids. So the grid, typically what happens in a building is that one puts the kind of the grid itself, or the building grid or the column grid, however you call it, over the building. And the kind of spaces or landscape around the building would be kind of designed by landscape architects. For us, that wasn't possible because first of all, the museum had two aspects to it. First of all, there was a museum which dealt with all the antiquities, and then there was something called the 24-hour museum, which is all the kind of landscape within its periphery. And that is in many ways the living museum, because that will be an open park which will be available as public space for one of the countries with the least amount of public space per capita in the world. So it was an important part to engage both local and international. But the long and the short of it is that we put the grid over the entire site, because that allows one system to capture within the entire museum, both landscape and building it within one holistic system. In some ways in the same way, in some, like the Nile Valley would be the kind of the irrigation system that was controlled by the state in order to regulate, to govern. The building would just then be kind of would use that grid to describe itself over the entirety of the site. So at any one point, anywhere on the site, whether it's a tree, a bench, a toilet, a plinth, all of which can be found within the grid system. So we can effectively, similar to the drawing of the kind of random circles, we can find anything anywhere at any one point in time extremely quickly. Overlaid onto that is something what they call the Nile Park. That was an important component of the brief. And the Nile Park for us is it doesn't kind of divide what is architecture and landscape. It merges the both together because it traverses both landscape and architecture without actually flinching. What the Nile Park does for us, the site is about a little bit over a kilometer by a kilometer. What it does, it then with the grid allows us to triangulate the whole site. So rather than doing contours, which is extremely geometrically heavy and very hard to locate and control, we can control the entire topography in terms of its ups and downs and a sectional condition with just a mere fragment of the number of triangles that are points that are needed to control it via contours. So this was very powerful because we were moving masses and masses of sand in large swoops rather than trying to kind of like shunt them around with tiny contour lines. In terms, this kind of begins to hark back. This is the plan of the museum with the lower portion being the galleries. This starts to touch back on the previous image with Palladio and Corbusier, where we have the kind of spacing of what is gallery and what is surface, what is gallery versus what serves there. The blue meaning being the kind of B or the surface zones, and the remaining space in between would be that of the galleries. This is actually the Francis Archer's sketch. He was just trying to figure out how to derive the grid, and he drew this on a BA flight. So he uses the waste bag on the BA flight, and on the flip side of it is Francis's Francis's sketch. I actually can't see that, but I think it says 240 at the bottom. That is something which is based on it's based on a European system, which is the number 12. The reason we use the number 12 is good for value engineering because it's the one number that has the smallest number with the maximum number of divisors. So 12 can be divided through 1, 2, 3, 4, 6, and 12. So again, it allows us to start to cut things like glass sizes, stone sizes, everything within the building to smaller sizes or increase them. In order to value engineer the project, but also to limit the number of redraws because we can subdivide and pretty much the building stays on grid. The trick behind this whole, the trick behind this is that part of the museum, let's see if that, oh, nope, there. We'll talk about that later, but the museum is actually formed off the two systems, one which is the number 3, which is 1200, the other one which is a binary system. And the grid that Francis drew didn't work in terms of the binary. So what we ended up doing is rather than 240, we used 384. 384 is something that would be divisible by 12 and is also a binary unit, which is divisible by 2. And so we have 384 units. So the trick with this, the trick with the plan is that we actually don't have dimensions on the entire plan. We only have a formula, which Francis says, all you do is you take the grid number, multiply by 25 times the unit. And the idea, if you can see, there's 1830, 1836, 1836, 1854, 1854, 1866, 18. The 18s are the digital streams or the service zones. The 236s, 254s, and 66 is actually the galleries themselves. So with that formula alone, one can pretty much know 90% of the dimensions in the plan without hitting it with a dimension string. So in order for us to do the project, rather than dimensioning everything, we basically gave the client a formula, which removes, I don't know, let's say 50% of the dimensions in the entire set. And again, it allows a very small office to kind of gear up and do very complicated, large, expensive buildings with minimum amount of draw time. So let's just say that's the grid. This was just a drawing. We put dimensions in to illustrate the fact that the formula actually works. And if I zoom in and zoom in, okay, so if I take grid line, you can see in the middle right, you can see S18. So if I take 18, which is the grid line, multiply that by 25, and multiply that again by 18, I get the number 8,100. You can see right there, the number next to S18 is 8,100. And you can pretty much go through the entire plan, and you will have every dimension without seeing a single dimension in the drawing. You just need the grid line, and you need to remember that previous grid prior. I mean, that previous formula prior. 25 times grid line times the unit. The roof does the same thing. It spans over different portions of the building. Obviously, the 30s and 36s would be the narrow span. The 54s and 66s would be the higher span. So the roof would need to get deeper as it moved towards the the primary grid line, which is the sectional conditions between desert and Nile Valley. So similar to that, I'm clicking on the wrong thing, is the roof. So when we sent the drawing finally over to Francis, I think actually Francis figured out the roof. But anyway, when we finally did sent over the final drawing to Francis, he just came back with an Excel spreadsheet and said, what are we supposed to do with this? He just said, double click on it. And pretty much because it is derived through a series of mathematical formulas, you can pretty much just run an Excel script and it will draw the entire roof for you. And obviously that means we can also modify it as much as we want. We can change the 36 to 242 or the 36 back down to 30 if we need to. And the Excel would just update automatically. Here's the building with the roof off. You can see the B, which is the service zones, and also the 236, 230s, 236, 54, 66 zones of the galleries themselves. And the roof would top the whole thing. So the biggest, most daunting task is this kilometer-long translucent stone wall, which probably was one of the things that won us the competition. But it was great that it won us the competition, but it was also very difficult to do. So what do we do? And this is actually a spin-off of a talk we did on weak stone. So fundamentally, translucent stone is terrible. It generally is used for things like vases, and it's a semi-precious stone. So at the end of the day, it's very weak. It was never meant to be used structurally. And what's interesting about the whole kind of journey was that because of its inherent problem, it no longer has a solution. And because it is problematic, it forces one to invent. And for us, that was the most enjoyable part of the project. How do we deal with something fundamentally weak? There's a large quantity of stone, approximately 4 football fields. You actually need 6 football fields because of the amount of wastage, but it's a lot of semi-precious stone. So in the end, we actually don't buy stone from quarries. We buy quarries in order to get the project done. So here you see onyx. We switch from alabaster to onyx. Alabaster is gypsum. Onyx is silicate, which is effectively glass. So it's a much stronger stone. So that was a substantial structural shift. It's translucent because it's illuminated from behind. This is one of the quarries that Bruno went to visit. So the first thing we had to do is you have to test longevity of the stone. So this is something we did in the UK at Briam, where we pushed the stone through, it was a halt. It's some kind of highly accelerated testing. And what this is simulates the effect of sand and wind and rain and so forth on the stone over a course of 50 to 100 years. If you look at the 2 squares in the lower right-hand corner, the top of the 2 squares in the lower right-hand corner is the stone prior to accelerated aging. And the one to the lowest, the one below that is the one post-accelerated aging. And you can see actually that the veins would open up. On the upper left-hand corner, you see a stone which should be used for construction, which is granite. And that stays the same. Nothing happens over the course of 50 to 100 years. This is the testing chamber that was being built, and this is a view inside, hitting with everything from sandblasting to UV, wind, so forth. The next issue is there's a stone, but there's also the steel that holds it up. This is just a comparison between the gem, which is the Egyptian Museum on the left, you see, and on the right-hand side, that's Koolhaas's Seattle Library. You can see the quantum of stone. It's actually a lot. It's substantially, it's a lot of stone. And the thing about it is the steel actually, oddly enough, cost more than the stone. So there was also a necessity to somehow economize on the steel. So one of the things that actually, one thing I should do, there in there originally when we designed it, there were, let me see, 2048, which is a binary number multiplied by 43 mega frames 2 times. There was 176,128 stones. That's a binary number. That's a lot of pieces, and people talk about CAD CAM and computers can do that, but at the end of the day, some guy has to go out there and figure out which of the 176,128 stones needs to be put where and make sure that's not put in the wrong place. So how do we look at economizing and reduce the draw time on this thing? So we're going to look at 1 mega frame, which is about 20 stories high. So what Francis came up with was he thought, okay, why don't we use a fractal system, a binary fractal system called the Sierpinski gasket. What that means is 1, 2, just think memory, 4 megs, 8 megs, 16 megs, 32 megs, and so forth. So what that means is we can then subdivide each mega frame by having the distance. Number 1 is structurally strong. He calls it a tennis racket. And simultaneously, every single one of these stones within the mega frame has the same set out. So we go from 176,128 pieces of different size stone to 43. That's what the fractal does. So again, massive reduction in draw time and coordination time. So if we go on from there, scale stone. So the subdividing has to do with bending the amount. What is it? L over at the bending. Something about bending. I forgot what the wording is. But if you have something, you actually if you have the length of something, its effective depth needs to be. It doesn't need to be as deep if it is stronger because it's shorter, and you keep on having and having and having, so that each steel is kind of increased in strength by having at every half point. So you keep on going down, and the halving actually has to do with the yield of the stone. So in other words, depending on the size of the stone, we have as needed. So if the stone yield was good, we have the amount of structure less. If with the stone yield is bad in terms of the overall size, we need to have the structure more. And it's a very adaptive system, so that because of the unpredictability of Onyx and we don't know what we're going to get, the whatever design that we draw can adapt to whatever yield is pushed out from the quarry. There's a series of tension nets that get strung in between, because for every kind of halving, which is binary, which flips 0 and 1 in and out, you're left with an open space. So there's a series of tension nets which deal with the weight of the stone, and 2 tension nets, another tension net that deals with the wind load as it moves in and out. So here's the steel frame. That's the primary cable, which is the dead load of the stone, and then there is the secondary cable, which deals with the wind that goes in and out of the page. And what we can do is that at a certain point, we can't have so much steel that you don't see stone anymore. But if one were to look at the stone itself, what is fantastic that Ed Forward at Arab actually came up with, he said at that point, the stone is strong enough where you can actually pin them. So the last binary subdivision of the stone, which takes the one triangle and breaks into 4, is just 4 pieces of stone without the kind of steel frame, but pinned to each other, so that they can fill the kind of frame of each individual panel. So we remove the steel at that point. And this is just one of his details showing how all the kind of triangles, 6 triangles come together. The different cables that slide through one another. Obviously, the cables can't rub against each other, so you can see in the upper right-hand corner the 3 red dots showing the different cables. 1 or 2 of them is dead load, and 1 of them is wind load. And that's just the clamping of it together. So the structural depth. The structural depth also works with it's not fully halved, but it has a kind of quality. It is somewhat halved. I guess you can say zero. If you start at 150 times 2 is 300. 300 times 2 is 600. Or if you take the whole 900 and you have it, you have 450 times 2 and you get 900. So for each of the kind of frames, the largest frame will have the deepest depth, 900. The next one will be the 750. The next one will be 600. The next one will be 450. And the last one will be 300 and so forth. So they keep on reducing it. They keep on scaling down in size. So again, it deals with some form of mathematical logic that does not need to see numbers as individuals, but as a formula, which means all numbers are somehow interrelated to each other. Thereby, a formula can produce all the numbers rather than having to represent individual numbers. A kind of tremendous sense of economy, and allows us to kind of manage the project. One of the things I forgot to mention is that the grid was not just something between us and Arab. We also work with Bureau Happold on the services, all the kind of endpoints for the water, electricity. So everything to do with the site, the structure, the architecture, the drainage, the electricity, the power, the roads, the slope, the water is actually on grid. And this is something we saw, and including that of West 8, who were the kind of landscape designers, who kind of, again, juxtaposed that of the Nile, the green, with the desert plateau. And the idea being that everybody works with the grid. So everybody stays within the kind of remit of the grid. And from a kind of checking drawings, from a coordination point of view, we don't look at drawings of structural engineer or services or landscape and see if they match our drawings. All we do is we actually overlay the any two consultants. And if they are off grid, meaning if we see areas which are slightly blurry, we know that area needs coordination because they're off the main system or the secondary system or the tertiary system. So we don't coordinate. We just look for blurry areas. And that pretty much allows to hit 80% of all the kind of coordination between the different disciplines. So you can see here the primary frame, the secondary frame, tertiary, and you just keep on going and it subdivides. So our coordination is looking for blurry stuff. So again, this is the binary, the binary system. You can see that the stone flips between inside and outside. So it creates really nice shadow. The Minister of Culture kind of was worried until we showed him, talked about that, and he kind of liked it. So that got us clear. So the last trip to Egypt, Francis did this drawing, which is really interesting. If you take the primary grid line that starts at the big pyramid, going through the roundabout, which is the 000 point, it goes through London, which is where the Arab offices are, and it ends up in Dublin. We know that the globe is round, but even then, maybe we were just destined for each other. Okay, so the Giant's Causeway, next one. So again, this is part of the Weak Stone lecture. The Giant, it's along the Antrim Coastline. There are more stones on the UK side, but the trouble is you can't get to them very easily. You have to go by boat. So this is actually the more popular one because it's quite easy to get to. The Antrim Coastline is a significant a heritage artifact. It's not just the stones themselves. The stones are have this unique hexagonal cross section due to the temperature at which the stone crystallizes when it hits the water. So the visitor center. So this is just saying that the UNESCO World Heritage Site is that kind of Antrim coastline. It's the entire coastline that runs up and down. There's a bridge on one side of it, which is fantastic. Not just the stones themselves. And you can see here that our project actually just touches that line that divides between the cliff and the edge that falls away versus the kind of fields at one point. So it's very sensitive to the coastline. Here you can see the project on, there's two buildings left and right. There's a hotel and a school, and down the middle is a path up to the point that touches the Antrim Coastline, the UNESCO World Heritage Site on the left-hand side. A folding up of the landscape to house the visitor center, and on the right-hand side, a folding down of the landscape to house all the cars, to hide 300-something cars, huge number of cars. Here are the two cuts in the landscape. One pops up, one goes down, up to house the visitor center, down to house the cars. Here is a view. The green triangle strip is the path up to the Antrim coastline, or that ridge line. Behind it is the visitor center, and to the right you can see the car park. On the other side, you pretty much have no building. So this is where the bus loop happens, which brings you down to the stones. On kind of tucked behind the bus loop on the left is where you come out to the stones. So this is kind of just touching on the kind of weakness of the stone to start with. I call it a contingent stone. It needs to touch 3 other sides of neighboring stones to stay up. You will never see a column of basalt standing vertically by itself, apart from maybe in China, where they have stronger basalt. And one of the key aspects of the project, which was fantastic, is the kind of the move by the client to say that we must source the stone locally, both from a sustainable point of view, meaning it's literally down the road, and when the opposite is we can get it for half the price in China and be 4 times the strength. And the other thing was that the building was meant to be part of the same flow, lava flow, that would be from the quarry. So there's something quite beautiful about the fact that they're the same stone, even though at the end of the day, who can tell? But there's something great about that. Here's the view showing the kind of basalt as they're stacked. So this is the critical thing. These are the joints. And again, it deals with the yield of the stone. It deals with where the joint lines are, how many joint lines we can allow for, and how do we come up with a set that both protects the client in terms of cost, given the kind of nature of the stone, and also at the same time deals with structure, its strength, its yield, and architecturally. So organize and subdivide. So the first thing we did on the left-hand side, visitor centers, on the right-hand side is the car park. The car park is this is just saying visitor center car park. But the key behind this whole thing is how we had to come up with a subdivision of the building. And what we did for the subdivision is we actually used the subdivision of the British Standards car park in order to describe everything about the project in terms of the visitor center. Because at the end of the day, if we don't get the car park dimensions right, we expand the car park, meaning if it isn't operating at optimal capacity, we run the risk of having too many cars occupying larger amount of spaces, which would again significantly impact the UNESCO World Heritage Site. We want to keep our footprints small. The visitor center, if it's off by a few mil, nobody really cares. So the whole building is structured off British standard car parks. That's the stone itself. So basalt. Basalt, here's the stone quarry, right around the corner, McConnell's. And then the thing about basalt in Ireland, the only thing that it's used for, because it is so structurally useless, is to grind it up and use it for aggregate in roads. That's it, nothing else. So how do we deal with something which is effectively utterly useless? So this was showing the compressive strength and the flexural strength of stone, meaning tension versus compression. The compression you can see is actually quite good. Tension is bad. It actually has nothing to do with the fact that it's good or not. It has to do with the line keeps on bouncing up and down. And because of that, it's terribly unpredictable. And because of that, we don't know what we're going to get. Granite would be straight. So how do we incorporate that as something that deals with the unpredictability or risk within the overall project? The first thing we did, because it is so weak in tension, we have to look back at the Greeks. So we are no longer cladding the building because it would just fall apart. We are just stacking lumps of stone. So every piece of stone is pretty much solid in that building. something that 2,000 years ago would build 3,000 years ago. But the trouble with our column is it has a slenderness ratio instead of 5 to 1, only 4 to 1. So it's easy to fall over. So what we had to do, again, something very weak, how do we invent something around it? So we stacked the stone and we put dowels in it and we pull the stone. So we simulate the dead load of the Doric column by basically pulling back at it. So again, so therefore in this particular case, it doesn't fall over because we are producing through pulling the kind of aspect to increase the aspect ratio, or rather make the aspect ratio better. So this is on the left-hand side, you see this, the joints, 150, 300, 450. That's the height of the stone. Obviously, we would like 450 stones because they're higher, less joints, much better. So our hope in the beginning was that we would have very few 150s and a lot of 450s. So everything seems very monolithic. We did not draw one facade for the client, because if we drew one facade, they would have the contractor would have kept on blasting to get that size, and that would have been an exorbitant amount of money. So we just said the sizes of the joints is dependent on the yield of the stone. So if you have not so good blast, you have more 150s and a little less 450s, and somewhere in the middle. So we keep going. And you can see with a really bad blast, we can have a lot of 150s and very few 450s. And you just increase the number of joints. And what's interesting about this whole thing, at the end of the project, there were 12 blasts in all. You can actually walk along the facade and see, that was blast 1, great blast. Oh, 2, getting worse. 3, getting really bad. And it just kept on degrading. And then we got some few blasts that were very good at the end. So the idea that the facade actually registers all 12 blasts, and not only is it part of the same lava flow, it actually is part of the same kind of yielding process, 12 blasts that would occur over time to build up that wall. Let me see. There's the 2 big holes, I think, are the pulling holes, and the one is a centering dowel. So there you can see the 3 rods that pull them together. We just put this in. We thought it was kind of neat. The building, as you know, is very trapezoidal. So rather than welding 4 pieces of steel, we thought it was kind of cool to simply take the same thickness of steel plates, shunt them, and bolt them together to create that column of the trapezoid. That's the view at night with the pathway going up in the middle. And the last project is a project we did for the Venice Biennale, and it was a project again working with a series of Arab, but this time also with Holger Folter, who was another engineer who was in the Dublin office at the time. It was about collaboration, and it's about every new project being a discovery where different people come together for the first time, doing something that nobody quite knows how to do, that's also way too big, and we somehow have to work together to figure out how to get this thing in balance. And this is at the end of the Biennale, the Arsenale, because everybody's tired, so we put a bench at the end. Oops. And let me just see if I can forward this. Out there. So that's on opening day. Now that doesn't work. There's too many people on the bench. We will move on to the next one. So you can see it's very quiet. It's nothing in the room. There's just one bench going across the hall. But when people start to sit on it, you can now see that it activates the bench. And it's 6 pieces, or a seesaw. But when one sits on it, every piece moves because they're all interconnected. So there's 6 benches. There were 6 consultants on GEM. How do we collaborate and make the whole thing come into balance? So that's the bench in section. That's the bench in its resting position. And that's the bench when it's in its activated position. So the whole thing activates and we don't know what it's going to go into. The most beautiful thing that was developed by Holger during this time was this notion of plastic versus elastic deformation. Effectively, what that means is steel, you can bend steel and it'll bounce back to its original point. But if you bend it too far, it deforms beyond that and it can't bounce back. So the key with the bench is that we have to stay within elastic deformation where it keep on bouncing back. It's quite beautiful. Very architectural. And that's the bench. You can see that when you sit on it, it bends, and you can see at the very center at the top where it begins to open up. And because the steel will pull, deflect and pull, it will pull that bench back to its horizontal position. It will tend to always go straight, provided it stays within elastic deformation. Don't bend it too much, in other words. So I don't know why I'm showing the same one there, but anyway, that's the bench. So you can see on the top is the 6 pieces. On the bottom, if you can make out a pink line, the pink squares links all the benches together. That means that one bench is actually 24 meters long because they're all interlinked as one bench rather than a 3 meter or 6 meter or 9 meter bench. So this whole notion that we are different, but we're all interlinked. How do we negotiate it? Here's it in section. Here's the kind of pin that kind of rocks back and forth. The great thing about this thing, the bench, was that, and I forgot to describe this in the previous image. The thing about what happens with the bench is people come and everybody sits down at the end of the Arsenale exhibition. One person will sit down. When somebody else comes to the end of the exhibition, somebody else, because they don't know that previous position, would sit somewhere else. What then happens is that the first person sitting down would end up bopping up because the other person would have moved one of the 6 benches. And then when somebody else sits down, the 2 people would bopping up. And depending on where you sit on the bench and which bench you sit, everybody would start to move and come into proximity, not because of intention, but because the fact that the benches are interrelated. It's like a bunch of consultants that never worked with each other coming together. And it's slowly over time that different people shift along the bench and jump up and down. You can actually get a dozen people together if they work together, and they very much find the motion, is they can get the entire seesaw to actually work. All 24 meters of it, you can get a dozen people who don't know each other to get the whole thing in balance so that it begins to rock. And that was effectively the whole concept of this collaborative spirit, this notion that different people come together, don't know anything about each other, but somehow you can very quickly work together to get things into balance so that you can rock the bench. So this is just an analysis showing that the trouble with the bench is that engineering programs make buildings not fall down. The bench actually works perfectly in failure, meaning when it rocks, it's actually in failure. So none of the engineering programs work. So they did all the calculations at the beginning by hand because they couldn't. Analysis programs don't calculate buildings to fall down. So anyway, so here's the calculations. And once we got it going, then we can pretty much analyze the deflection within each of the pieces. We just like that drawing. And there shows the kind of, this is all staged, so people look kind of good and in control, but they're not until they get balanced. And then we had to build it. We sent the drawings. We went to Germany. We spoke to a bunch of people. And you can see, again, you have to track the pink line at the bottom drawing. You can see that the pink line zigzags up and down. It's one continuous line. And what happens in Germany, though I can't see it, they actually, because of the risk involved, which is probably a smart move in the end, they severed all the links between the benches so that each bench was linked, but each bench balances itself. So they removed all that plastic elastic deformation thing where all the benches work together to pull things together. They basically balance each bench by itself. They're still linked. So, but anyway, they did a beautiful mechanism. Germans like their machines. You know, everything's mechanically. It's absolutely brilliant. That's the bench being made, or seesaw, however you call it. That's the mechanism. It still works. It's worked for, it only got dismantled last year. Different clients take it and put it in their offices. God, must have been, it's 10 years old at this point. It's still working.
7.
7 years. It's like white, you know, BMW motorcycles. They keep on working. It's still working. And that's the end of the talk. I am 4 minutes under.
Thank you very much for your lecture. It was incredibly interesting insight into your work and incredibly in depth. Thank you so much. We have a couple of questions which have been sent through by some of the audiences and have been collected through Instagram. And it'd be great to hear your ideas on them. I'm going to just jump straight into it. So the first question relates to some of your projects which work in more historically sensitive sites, especially restoration projects. And the audience member would like to know sort of what are the most crucial design decisions that you need to take into consideration when working on areas and projects and sites of historic significance?
I think we say with the National Gallery of Ireland, or we say with the Trinity project, it was trying to find almost its special voice, or trying to find something that was very particular. So, for example, with the National Gallery, it's not a perfect gallery by any means. It's kind of developed over years of history, and when we started, we had this tendency to almost flatten it, to make it more perfect. There were so many really annoying things. You're like, oh, for God's sake, why couldn't they just straighten this out? And then we eventually came to the realization that actually it was letting those things happen was maybe, and not just maybe just accepting it, but allowing those moments to occur and then working with them and finding a way to deal with them was quite important, which in a way kind of goes against just everything we've talked about, which is this grid that kind of comes over everything. But even at the National Gallery, we had a grid, but it was then how does it start to interact with what's already there? But for us, I think the most particular point of these older buildings is just almost finding what's so special about them and then seeing, can you heighten that or let it happen?
Thank you. Shih-Fu, would you like to add anything?
Yeah, the odd thing about conservation is that I once wrote a paper and for Colin Rowe, and I submitted it and I got an A on it. And then I took the same paper and submitted it for Douglas Evans, and I failed. And the thing about all of this with conservation is that it's the same thing which happened with the National Gallery. I think the Guardian wrote something on it, and it was not too great. Somebody else wrote something on it. I think Edward Said or something like that. It was fantastic. Yeah. And the odd thing about conservation is that it's quite subjective, and it does vary what cultural context you're in. In places like Germany, where the war has obliterated entire cities, the extent of kind of restoring what's there has gone so far that it often has been criticized as too Disney-fied because it looks so much like the original. And the other extreme is do you see conservation as an opportunity for the architects, for the new, the current design, to do something completely new that adds to the history? So I think for us, the challenge, though, there is no answer. It's really at the end of the day a position, and it will vary between cultural context. It will depend on who's looking at it. And the challenge really at the end of the day is just finding the balance where we at this present moment in time would like the degree of newness, or how much should we preserve the degree of oldness. And that in itself is a very interesting decision during the course of the project.
Thank you. Yeah, I think one of the brilliant things I love about your work, and from listening to the talk, is how you are able to work with historic fabric in a contemporary way. And I think hearing how important the grid is to some of your projects helps me to understand a bit more about how your working process works in that way, and how you are able to find contemporary and new moments or geometries in these historic buildings. Let me get up the next question. So we've got 4 very different questions here. So the second question changes the topic completely, and with the audience member would like to know about your thoughts on the pandemic. So as how our cities have changed, the way we live and the way we work, and also interact with each other. What are your thoughts about how the pandemic will affect architecture?
I think in the city, maybe there's been a real appreciation of public spaces. So, I mean, that's kind of obvious, but hopefully that will continue. I do wonder a little bit whether in terms of where people live and work, if there will ever be maybe a scaling, whereas right now there's the big centers, everybody going into the big centers, where there be a bit more scaling, with the recognition of how much is possible digitally, where there might be smaller clusters rather than those mega centers. For architecture, Shih-Fu, I don't know if you have any thoughts. I suppose in terms of residences, it's kind of the obvious thing, I suppose, in terms of an appreciation of the outside, and maybe the necessity of building spaces that people can actually live in, as opposed to just sleeping in, the micro units. But they're kind of my thoughts, Shih-Fu.
The only thing I have is that one of the consultants on one of the projects we're working on in the US said to us, when the pandemic hit and the lockdown happened, all the projects stalled for a few months and slowed down. And this project just kept humming along as if nothing happened. And it's sort of like, from what I understand, after 9/11, the entire banking industry basically reconfigured themselves so that they're completely remote, which means when the pandemic happened, it affected nobody in terms of how they work. Everything just kept on moving smoothly because the entire system was set up to work remotely because they had to. You can't stop the financial system. So the only thing I can imagine is that people don't have to fly everywhere to do everything. It's just so much carbon. And it's a phenomenal how much. I mean, we've been doing this since 2003, screen shares. I mean, I can design entire projects on annotation. We can do so much with so little carbon. And I just hope that the world sees some value, is to get something out of that and changes how they work. And that kind of addresses also the sustainability side. Can we just think a little bit more about how we work? Because quite a lot actually has been done, and a lot of people didn't even know this technology can do what it can do.
Well, I mean, on that point, I mean, you did mention just then, and also in our chat just before, that your office has been working with Zoom or digital conferencing technologies since 2003. So maybe you have some advice about what strategies they can adopt, or processes that for some practices who are sort of struggling to shift to working online.
I think everybody's pretty much caught on at this point. 9 months of Zooming, I think everybody's a pro.
Well, then let's go straight on to the question of sustainability then, as you mentioned just then. So the next question asks, what are your both your sort of key issues at play in terms of sustainability and climate change for architects over the next few years?
There's one thing about working with older buildings in that you realize if one of the most invasive things we can do is to build, then we should be building better each time we do it so that the impact is as little as possible. So I think, really getting what we do to make it the best it possibly can be so that it doesn't have to get done again, so that it can change, so that it's loose enough. And trying to do as little as possible every time we build. How much can we not build? Like, in a way, how much can you do by not enclosing space? If you think about, we say in these islands, in the British Isles, can communication sometimes be outside? It never gets so cold. Just really trying to interrogate. So you try to as little as possible. And I think sometimes just that emphasis on interrogating every element that you do before you start all the add-ons about which technologies are going to add on, but trying to emphasize to focus on what we do. I think we could make quite a big impact just doing that.
No, I don't have anything significant. No, I not really. I mean, it's just a general comment. I mean, at the end of the day, though it serves its purpose, iconic architecture is fundamentally the most unsustainable thing we can do. It is predominantly performance, and for performance, it needs just tons of stuff and carbon. Which is not to say that we don't do it. I mean, Egypt's iconic. I mean, we do need our specials. But I somehow think that there's just this desire for this is a gross generalization, but there's a kind of desire that to be a good architect, that we need to achieve these wins and build these icons. And yet they completely scream of unsustainability, that there isn't beauty and merit in saying that at the end of the day, the 90%, the 98% that isn't iconic, it's not glamorous, but that is where the strength could be. That if we hit not the 2%, which are fundamentally unsustainable, and we somehow put all of that energy to the 98%, that maybe we can make a difference, and that difference will be huge because there's a lot of percentage of non-iconic. And the one area that is the 98%, which I think is what people have done a lot with, really, and really just be applauded for, is housing. Housing is part of that 98%. That which is not glamorous, it's not wealthy, it's not money, but that's just part of everyday life. And I think the fact that universities can't do housing and concentrate on housing, I think that's a great thing to promote. And somehow just switch away from necessarily that the only thing you can be to be a successful architect is to build an iconic building and use tons of carbon.
Well, maybe your answers to that question sort of tie in quite well, or sort of cross over with the next. But do you each have sort of a thought about what's important for the future of architecture?
I do think that maybe if I could adjust the question a little bit, maybe thinking as a younger architect, that maybe over the last 20 years, there has been a real focus on working on those very, very glamorous projects. I do think that thing about the nuts and bolts, the ordinary, needs to really have the value, because that is what is the stuff of our lives. I mean, and I think for architects, that being valued rather than just the big glamour projects is terribly, terribly important. And, you know, we all have to try to do the best ordinary we can. I mean, that's not devaluing the ordinary.
And though I don't have an answer for the future question, it's almost too general. In some ways, maybe that's why we do well with renovation, because yes, it is glamorous to do the National Library, National Gallery of Art, or the Trinity, but at the end of the day, there's nothing glamorous about it relative to us. We just take what is amazing and we let its original authors come through. Our role is only the support of that. And to a large degree, it's the belief that being that layer that's underneath all the celebrities is every bit as important in terms of both the fabric as well as supporting those projects that are already glamorous. And maybe there's even to pull it into sustainability, and maybe there's something sustainable about that, because at the end of the day, if they are iconic and you support it and you make it live again, that's just as much an iconic project as having to build a brand new one with tons of carbon.
I think those are both absolutely beautiful points, and especially beautiful points to end on after that lecture. You know, great hopes for the future to work more with historic buildings and to embrace the everyday and the ordinary and to bring out the best that already exists. Thank you so much for your time tonight, and we look forward to seeing more from your practice.
Thank you very much.